Aha, we're online. Okay, so welcome everybody. Good to see some people back. And Rob, how are you doing?
You're good, thank you.
Matt gave a very nice talk a couple of weeks ago in the CMS over there, and he's going to give us our own instalment on time-dependent conformal mappings for sloshing problems. So over to you, Matt.
Thank you, Darren, and thank you everyone for coming, and thank you for those who are watching on demand. Okay, so yes, this is a talk. I'm going to talk about use of time-dependent conformal mappings in fluid mechanical problems. So any of those who did see the talk in CMS, I apologise for the little bit of overlap, but I'm going to try and give a slightly different flavour in this talk than I did in that talk. But again, I'll start just by highlighting my collaborator, so Tom Brickers and I worked on much of what you're about to see in this talk. Okay, so I'm not going to really talk too much about the motivation, but I do need to just highlight the type of the problem that we are intending to solve. So this is an example of the problem we're interested in solving. So we've got some rectangular vessel, in this case, which is filled with some inviscid, irrotational, incompressible fluid, and we're going to confine our motion to just two-dimensional motion. So you can think of this as being a rectangular vessel going in and out of the board, and the profile that you see up there is repeated in and out of the board. Okay, so here's the type of thing you might have. So you'll have some rectangular vessel. I'm going to normalize it so that it's got length 1, so this is x equals 0, x equals 1. It's got a flat bottom at y equals 0, and it's got some unknown free surface at y equals eta of x and t, and this free surface is unknown, and we can solve for it as part of the motion. And we can think of this vessel as perhaps being on wheels, and this f of t could be one of two things. So you can think of this as being some prescribed forcing, so you've got some vessel on wheels, pulling it and perhaps pushing it backwards and forwards harmonically with some given frequency and amplitude. Or you can think of this vessel as being perhaps attached at a spring on this left-hand side, and then attached to a wall, and then perhaps I then pull that vessel back and extend the spring and then let it go, and then that vessel will oscillate backwards and forwards under some motion. And in that case, this f of t won't be prescribed. In the case where you're telling me what the amplitude and frequency is, it's a prescribed f. In that, the other case where perhaps it's attached to a spring, f of t needs to be solved for as well. So it'll have its own differential equation for solving f of t. I guess for the first part of the talk, the key thing is just to think of this as just being some prescribed forcing, but it could really be either. Okay, so in anticipation of using conformal mappings, we're going to extend our domain. So from x is 0 to 1, we're going to extend it to being x between 0 and 2, and we're just going to take the even extension about x is 1. Okay, so we're just going to map our domain, mirror our domain in x equals 1 in order to utilize conformal mappings, because that then ensures that we have periodic free surface, periodic domain. Okay, so we're going to solve some differential equations. So we've got incompressible irrotational motion, so our fluid can be written in terms of a velocity potential phi. So phi satisfies Laplace's equation in our unknown domain shape. So from x is between 0 and 1, and y between 0 and this free surface. And we've got two boundary conditions on the free surface. So we've got the kinematic boundary condition. This tells us that any particles that originate on the free surface stay on that free surface, and this can just be written as this equation, so d to dt plus phi of x, eta of x is equal to phi of y, evaluated at the free surface, and all the way, well, so I guess you can think of this as being extended really now between x's between 0 and 2. So this is the original domain, but obviously we've extended it, so this is between x's 0 and 2. And then we also have a dynamic boundary condition, so this tells us that pressure must be continuous across this free surface in the absence of surface tension, which is another assumption we're making. And that just gives us a Bernoulli type equation, so phi of t plus these nonlinear terms, plus this gravity term. So of g of eta minus h0, so h0 might be some mean depth of our fluid or just some constant. And then this is where the forcing comes in, you have an x f double dot term. So this will be what the Bernoulli equation looks like between x is 0 and 1, and then because we've made this even extension, it just changes ever so slightly in this last term for the range between x's 1 and 2. Okay, and obviously we've got the usual impenetratable boundary conditions on the wall. So d phi dy is 0 at the bottom, and d phi dx is 0 at the walls, which are x equals 0 and 2. And because we've made this even assumption on our domain, we made this even extension, we also get the condition x equals 1.
Can I ask a question?
Yes.
This term x, f double dot,
Yep.
it depends on x.
Yep.
Do you want to just explain it for me? Is that obvious?
Is it obvious? Good question. So it is, but yes, off the top of my head, I can't quite remember exactly now where it comes from. But you're right. It's a multiple of x, and if you have a forcing in the y direction, you just get y times some. But yeah, I'll show you when we get back. Okay, and if f is not prescribed, then f has some additional ordinary differential equation. So I'll come back to this at the very end of this talk. So these are the nonlinear equations we want to try and solve numerically. So that's difficult to do because we don't know where this free surface is, and we will have to find it as part of our solution. Typically, numerical schemes work really well when you have some fixed domain, and then you can easily put down grid points or grid points around the boundary, whatever. And that only really works on fixed domains. But because we've got this domain that changes as a function of time, we can't really do that in its current form. Okay, so what we want to do is we want to introduce a mapping. So this is an example of the sort of domain that we've got. So there's x is 0, x is 2, so I've made this even extension. There's our variable bottom at flat bottom at y equals 0. And then you get sort of a even extension, so you've got this periodic free surface. This should be 0 derivative here. It's just my poor schematic drawing on xfig rather than anything else. So this would be have 0 derivative here. And we want to find some mapping that maps this domain to a rectangular domain such that the corners of the 4 domains get mapped to the corners of this rectangular domain, so A goes to A bar, A prime, etc. The sides, x equals 0 goes to some new variable, mu is equal to 0, and x is 2 to mu is 2. The free surface gets mapped to the flat surface, mu is equal to 0, and then this bottom at y equals 0 now gets mapped to a flat bottom at nu equals q, and q is a function of time, i.e. as this free surface changes, this will get mapped to a rectangular domain, but the aspect ratio will change. The aspect ratio is a function of time. This q of t is obviously the conformal modulus, and it's not known a priori, and we have to find it as a function of time, and we find it because the free surface is not known a priori, and it varies the function of time. Okay, so let's just set the problem up. So our physical Cartesian coordinates, x and y, now become functions of these new variables, nu and mu, and a function of time. So we get these new variables, mu, and t, and x is a function of these, and y is a function of these. So the mapping we want to use is conformal, so it satisfies Cauchy-Riemann equations, and because of that then both x and y satisfy Laplace's equation, and this will prove useful later when we look at the solution procedure. And just a little bit of notation. So I'm going to define capital X and capital Y as being the values of x and y evaluated on the free surface. So that's along mu equals 0. So it's just going to be capital X and capital Y. And the same thing for the velocity potential phi and its equivalent stream function of psi. So I'm going to say capital phi and capital psi are the phi and psi evaluated on the free surface. Okay. So this x and y gives us now a parametric representation of the free surface. Proves useful. Okay, so taking those original boundary conditions that we had, if we write those free surface boundary conditions in with these new x and y variables, the kinematic boundary condition becomes the top condition and the second condition. This is Bernoulli's equation. Obviously, I'm just using one of the Bernoulli equations. It doesn't really change very much in the x's 1 to 2 range. So this is the form it has, just so we can get an idea of what these equations look like. And here, J, this is just the Jacobian of the mapping. The bottom boundary condition was that there's no penetration of the fluid at the bottom, and it just then becomes the deep side. Mu is equal to 0 on that bottom, or psi is a constant. Okay, so psi is a constant, so it's a string function, a string line, which is what we expect. Okay. Now we've used this conformal mapping, ultimately what we want to do is we want to integrate this equation, integrate this equation. These are both time-dependent equations, you see the time-dependent terms in there. We want to integrate those forward in time and find what x, y, and phi are and how they evolve in time. But that's difficult because if you look at these two equations, the time derivatives are implicit in these two equations. So you have a y of t and an x of t term on the left-hand side, and here you have a phi of t term, but then you have an x of t and a y of t term here, which makes just using your favourite time integrator such as Runge-Kutta a little bit difficult. But what we note is that if you've got any point in space can be written as a linear combination of two vectors, as long as they're perpendicular. So here's two perpendicular vectors, dx du, dy du mu, and its normal vector dy du mu. Dx du mu is two perpendicular vectors, so we can write any point in space as a linear combination of these two vectors. So let's write the point x of t, y of t, so it's a linear combination of these two vectors, where alpha here and beta are just, at this minute in time, unknown functions of mu in time. Mu, we're on the free surface, so mu in time. And I just put over these Jacobians of the mapping just for ease at this stage. Okay, so if you take these two equations and substitute it back into the kinematic boundary condition, what you find is that beta is equal to minus deep side mu. But you don't get any information about alpha at this stage, so alpha can be thought of as the tangential velocity at the free surface, and it's unknown at this stage, but we're going to fix it later by forcing our transformations that we're going to introduce in a moment to be analytic. Okay, so we're going to introduce some transformations between x and y. We're going to need those to be analytic, and that then gives us a representation for alpha. Okay. And then substituting both of these two forms of x of t and y of t into the dynamic boundary condition just gives us a dynamic boundary condition that looks like this, and I realise this form, this is off the forcing, there should be a plus x minus x plus xf double dot term here as well. So the forcing is still here, just taking it out from a different paper. So we now have a PDE that we can integrate for x, a PDE we can integrate for y, and a PDE we can integrate for phi. But the right-hand side of phi and x and t and y and t contain psi, and we don't have a PDE for psi. We have no PDE that we can advance in time for psi, so we can't directly integrate these equations. And also we have this problem that we need to determine the form of alpha. So this is where our complex analysis is going to come in, because we're going to make use of the fact that we have these two analytic functions, z, which is x plus I, y, and the complex potential w, which is phi plus I psi. So these are our three equations. We're going to come back to these in a moment. We're just going to do a little bit of complex analysis and conjugate harmonic function. So some of this may be very straightforward to many of you, I'm sure it is, but for my sanity at least, my complex analysis is not as good as probably everyone else in this room, to be fair, but my complex analysis is not as good as that, so I just want to go through it just for my sake more than anything. Okay, so let's consider some general analytic function. So we've got u plus iv there, and we're going to consider it in a slightly simpler domain. We're going to consider it in the half space, so we've still got nu between 0 and 2, but now nu is going to go to minus infinity. I'm going to remove this conformal modulus by setting it equal to infinity. And so this is the infinite depth case of the problem that I originally posed. Okay, so now we can take this domain using this mapping. Psi is e to the minus I pi plus mu plus I nu. This then maps that domain to the inside of the unit circle. So then we can write down Cauchy's theorem in the unit circle. So you have u plus iv anywhere in the unit circle is written as this integral over u plus iv on h of the circle. Okay, happy with that. So here I'll use again the notation capital U and capital V are u and v evaluated on nu is equal to 0, which is equivalent to the h of the disk. Okay, we're all happy with that. So why is this useful for what we want to do? Well, because this holds everywhere, it also holds on the edge of the unit disk. So using the Shockley-Flamel approximate or formula, basically remove that 2 and we can evaluate this on the edge of the unit disk. And so if we do that, and we do a little bit of manipulation, algebraic manipulation, we have an equation which relates capital U and capital V to themselves under this integral. Or it can be written in this complex form where this capital K is this principal value integral operator and is it's the integral form of the Hilbert transform. And these bar terms, these are just the mean value of these functions between 0 and 2. Okay, so we have, this is now, as we now know this is true, if we take the real and imaginary parts of this equation, then what that gives us is a relation between V on the free surface or on the edge of the disk, and it relates to the Hilbert transform of U. Similarly, U is related to the Hilbert transform of V. The key thing here is that if I know one of these functions, if I know the real part or the imaginary part, then I get the other one using these mappings. So if I know V, I get U using these mappings, and vice versa. So that's the infinite depth case. So how does that then relate to what we want to do in finite depth? Well, the problem is exactly the same, except now you have you don't have infinite depth. You have a region of space that when you use that exponential, when you use this exponential mapping, it maps to an annulus rather than the inside of the disk. Again, you write down Cauchy's theorem. It now has a contribution from the free surface out on the outer edge of the unit circle, and it has a contribution from the bottom on the inner circle. So you now have two equations, but that again must be true on the outer disk and on the inner disk. So you do the same process. Instead of just one of these equations, now you have two equations. And it looks a bit like this. So now you have two complex equations that relate U and V on the free surface to U and V on the bottom. So the subscript B means I'm now just evaluating on the inner circle at which is equivalent to nu is equal to minus Q. I haven't written down what R of Q, so this K is our usual Hilbert transform. I haven't written down what R and Q and S of Q are, but they're just integral transformations which depend upon Q, and they contain terms like hyperbolic tanh of pi Q and hyperbolic cosec of pi Q. And I'm going to come back to this in a bit. I'm going to think more about how we actually numerically evaluate this in a bit. But the key result here is the same, is that if I know two of these functions, i.e. if I know v and vb, then I can use this transformation, this Hilbert-Garrett transformation, to find ub and u. So again, I've got this link between these quantities. If I know two, I can find the other two. In many cases, I don't necessarily want to find the other two. If I know two of them, I just want to find u on the surface. Usually, I can do it via this map. Okay, so let's return to the fluid problem. Just briefly. So we've got two problems. So we want to use this mapping. We've got two problems. One, we can't find alpha. Two, we've got no equation for psi. So how do we determine alpha for this problem? Well, what we can note is that this function z of t over z of zeta, where zeta is going to be mu plus I mu, this is an analytic function in our domain. And if you calculate the boundary value, values for this, so you rationalize the denominator, multiply by top and bottom by its complex conjugate, etc., use those equations we wrote down before, and you can show that the imaginary part of this quantity, when you evaluate it on the free surface, is just psi mu over j. It comes from the kinematic boundary condition. And you do the same calculation again, but this time you evaluate it on the bottom, and you get it equals 0. So this is an analytic function where I know the imaginary part on the free surface, and I know the imaginary part on the bottom. So I can use this transformation to find the real part on the bottom and the real part on the free surface. But the real part on the free surface, so I only wrote down the imaginary part here. If you do this calculation and look what is the real part, well, the real part is just alpha over j. So if I use this Hilbert-Garrett transformation on these two functions and look at the real part on the free surface, then I get a form for this alpha over j. So in that case, alpha over j just becomes its mean part plus this operator, and this is the imaginary, because the imaginary part on the bottom is 0, that is that VB is 0. Write down the terms you have left is you have this operator k plus rq acting on this function here, which is which is v on the free surface, and then we write that as some alpha bar, and we just write this operator here. Just write it as tq inverse. Can't remember why the inverse comes from. I think we were using notation from somebody else who writes that this is the inverse, this inverse operator. Anyway, it's some operator acting on psi mu over j, and it's very easy to show that this alpha bar is 0. So what has this told us? This has told us what the form of alpha must have. So I have to be able to calculate this inverse operator, but as long as I calculate psi mu over j is, I let this operator act on it, and then I have alpha. I'm going to say a bit more about how we actually evaluate these operators in a second. Okay, so also with this Hilbert-Garrett transformation, we can actually relate capital X, or capital X minus mu, to capital Y minus mu. Those are our two analytic functions there. But this is evaluated on mu equals 0, that's why there's no mu appearing in there. Y minus mu with mu is 0. But again, you got the same thing. These two things are related by this Hilbert-Garrett transformation. X minus mu is tq inverse on acting on y, and psi is then just tq, so it's the inverse of this operator, acting on phi. So we now have an equation, a way of calculating psi. Okay, so before we had 3 equations, we had an xt equation, a yt equation, a phi t equation, no equation for psi. we now have these mappings, these conformal mappings, which allow us to get psi from phi, but we also have a mapping now which allows us to get x from y. So what people tend to do is, rather than integrate both the x and y equations, they tend to just pick one. So I'll pick the y equation, and then I'll use this transformation to get x. So these are your two equations you now solve using your favourite Runge-Kutta integration scheme, or whatever you prefer, from some initial condition. I don't know, some maybe if f is a force, a given forcing, then you might want to start from just a quiescent fluid, and then you start forcing it, and you just discretize the free surface like this. So the idea is, how does the scheme work? So you've got some initial condition. Given this initial condition, you can calculate psi, so you can calculate this psi nu over j. You use these operators and get what these terms are in terms of what. You do these numerically, so you get numerical valuations for these two terms here. Then you can integrate these two equations to the next time step. And once you've integrated these two equations, you then use this operator to find x and this operator to find psi. It's not quite as straightforward as that, because you've got this conformal modulus q that I said you don't know a priori, and you actually then have to do this process. So this time stepping is fine, but evaluating these operators requires an iterative process. You have to keep iterating and updating your conformal modulus such that you conserve mass. Okay, so how did we do this? Well, actually, you had those nice integral representations for this, these operators. It turns out you didn't use that. You can do it that way, and I did sort of play around with it. It's a little bit awkward, but in this doubly connected problem, it's actually easier to just solve Laplace's equation. So x and y both satisfy Laplace's equation, and so does phi and psi. So it's really easy. You're in a rectangular domain. You just solve Laplace's equation. You satisfy your boundary conditions apart from those on the free surface. And this is the sort of form that you get for x minus mu and y minus mu. You get these nice Fourier series representations. And the Hilbert-Garrett transformation is sort of hidden in here. And it's hidden in here in the sense that, how do we do this then? Okay, if I give you y on the free surface, so I put in mu is equal to 0 here, then this just gives me a tanh n pi q times a n of t times cos n pi mu. And I've got y evaluated numerically. That's valid. I've got that along my free surface. So what I do is then, we can take fast Fourier transforms of that numerical form that we have. Essentially then, that gives us the combination of these ANs. It gives us the values of these AN of t times tanh n pi q, multiply these by these cosine terms. If I evaluate this on the free surface, then this term is just 1, so I get AN of t times sine n pi mu. But I know what these ANs are now from this term here, so I can reconstruct in Fourier space this combination, and then I take fast Fourier transforms to get me back out and gives me x and t. So I'm not really doing these conformal, I'm not really using these integral forms of these conformal mappings, but I am using it, it's hidden in here. And if you look at how those integral forms modify Fourier series, if you let them act on the general Fourier series, then you'll see these tanh n pi q terms coming. And again, I just reiterate, you then iterate this mapping such that you update q such that this mass is conserved. Okay, so
Just the quick question, is it the same coefficients in both of those, or are you just doing, is there a b end here?
no, they are the same code because that's right. So that's the case here for the flat bottom. You don't have any bn terms. They're sort of given some specific value because you've satisfied that bottom boundary condition. That's why it's so nice. That's a really good point. Then come on to the next slide and then I'll talk about it. So I've just plotted here just some profiles here of what the free surface looks like as an example to show you. I don't really want to go too much into the fluid mechanics, but you can see an example of what these profiles look like. Small amplitude, they're symmetric about the centre of the free surface, and as you get larger amplitude, you get steeper waves. But that was a good question, and that comes on to the next slide. So for a flat bottom, you get these nice looking Fourier series profiles. If you have a variable bottom, you're right, you get an extra coefficient in here, and you have to then determine those coefficients by forcing it to satisfy your bottom boundary condition. That's a little bit of extra work, but not really that much extra work. You're just doing an extra iteration in Fourier space to calculate these beings. And that sort of relates to this question. So you can use this technique, as Darren asked, really, you can use this technique for doing variable bottoms. You just have this extra equation you need to iterate in Fourier space to make sure you satisfy the bottom boundary condition. You have an extra B of t, if you like, sitting in your map. But other than that, it's all exactly the same. And what's nice is that your phi and psi equations don't change because psi is still constant along this variable bottom. It's still a string. In fact, those equations are exactly the same. So it's only the x and y mapping where the bottom effects are really seen. So this is an example of just a variable bottom. So you've got sort of like a cosine step here. These are horizontal velocities. So it's positive in this direction, negative in that direction. These are vertical velocities. And you can also do other surface shapes of bottoms. You've got humps. We tried conoidal functions, so you have a more of a flatter bottom and then steeper at the edges. And we played around with it. And these are all doable numerically. Okay, but what I really want to say a bit more about in this talk than I did on Monday is what happens when you include baffles. So Darren Cohen gave a nice colloquium talk at Surrey when I was there, just before I was going on sabbatical, and his talk about these Schottky-Klein prime functions inspired me to try and see whether we can do anything with this problem. So the problem's almost the same as the one we've been considering. There's our rectangular vessel, there's our flat bottom, but now I want to put in these infinitely thin but finite length baffles at particular places on either of the side walls of our vessel. So here's our unknown free surface. I'm going to call it f of x here, as always happens as mathematicians. We do some slightly different work and we change all our notation to keep all other mathematicians on their feet. So I apologise about that. So now I'm going to have the free surface at y is 0 and the bottom is at minus LH. So you can think of L just being 1. I'm just going to normalise with respect to L, non-dimensionalise, sorry, with respect to L. So we're going to go from 0 to 1. And just to be awkward, this time I'm going to take the even extension about x is 0, so I'm going to go to minus 1 and 1. But this is, as I say, we all do this just to keep everyone else on their toes, right? Okay, but it doesn't really change too much. So in this case, what do we have is, I'm going to just, okay, so let's just introduce some notation first of all. So this time, I'm going to use this notation. So x and y evaluated on the free surface. So again, this free surface, we're going to introduce some mapping, which maps this free surface to nu is equal to 0. That's still the same. And I'm going to let x naught and y naught be those values on the free surface. I'm going to let xn and yn, with n going from 1 up to capital N, those are going to be x and y evaluated on each of these baffles. So this is baffle 1, so this would be x1, y1, baffle 2, x2, y2, dot, 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 dot. This would be xn, yn. And these will either be between minus some ln hat to ln if they're on this side. And you take the even extension, they just go maps a little bit further that way. Or if they're on this wall, then the image maps to the opposite wall over here. I'll show you a picture in a second. So those are going to be xn. And then xn plus 1, yn plus 1, well, those are going to be x and y evaluated on the bottom. Okay, so that's notation I'll try and remind you of this as we're going along. So here's what we're going to do. So we're going to map the domain like we did before. Here's our original domain. So I've taken the even extension, so here you can see this baffle's extended this way, so you get a baffle in the middle, here you get a baffle in the middle, and then B2 is split because it's periodically extended between -1 and 1. But we're going to wrap this around so those two bits are going to join up again. So now we're going to define our mapping. It's going to map this domain to this psi domain. So the free surface goes to nu is equal to 0. The bottom goes to nu is equal to h. There should be hats on that. There should be hats on these variables. Why are there hats on these variables? Well, in the same way that when we mapped our domain to our rectangle, we had that q of t that was our conformal modulus we had to find. In this case, this h hat is again our conformal modulus, but we also get conformal moduli for each of these baffles as well. They don't go to the same height as they originate from, and they're not the same length as they originally are. In this map domain, they're a slightly different length, they're a slightly different height. And you have to find those as part of your mapping. If this free surface was originally flat, then yes, they map to the same height and the same length. Okay, so then we're going to map this domain to, using our exponential mapping, it maps to the inside of the unit disk, or the inside of this annulus, sorry, and these baffles get mapped to slits that are situated either side of the real axis. They're symmetric about the real axis. So these slits on this side, these are those baffles that come from the center, and then this baffle is the one that comes from these two bits on either side, and they get mapped along this. We've got this branch cut along the negative real axis. And then we can map from this domain to this circular domain using these Schottky-Klein prime functions, these nice MATLAB routines that Darren and his team put together. It was only because of these things exist that I thought I can tackle this problem. If Darren hadn't done the hard work beforehand, I would have said, well, that would be a nice problem. Maybe I'll leave that for a bit. Because actually, without that, there's no way really of doing anything analytically. You have to do everything.
A few of those slits circular arcs.
Yes. Yeah. So these are now just, yeah, as you say, these are just circular arcs, and you need to determine the sort of the length of them and their position on the axis. Again, that's sort of the mapping of these conformal moduli that's up here, and they relate obviously to the radius and position of these circles.
So the one in the top right to the one on the bottom left.
Sorry.
The one on the top right,
yeah.
Yeah, to the one on the bottom left.
Yeah.
That's the same exponential.
That's the
mapping.
same exponential mapping. Yeah.
Right.
That's the same one we've seen before. So if you didn't have these baffles in, then you just map to the unit circle with the center circle removed, and that would be the bottom. Okay. So then you have, so obviously then you have to use this extra mapping to get us to this circular domain. And why do we want to be in this domain? Well, we want to be in this domain because then we can use Cauchy's integral theorem. So again, here's our Cauchy's integral theorem. I'm going to write it down again. So again, we'll use the same notation. So this kappa is x minus mu, and its imaginary part is y minus nu. And I'm going to call those two things x tilde and y tilde, just to save a little bit of algebra. So like we had before, so when these slits were missing, as I said, we used Cauchy's integral theorem, and we had a contribution from the edge of the disk, and we had a contribution from that disk in the middle. Now, in this domain, we have a contribution from the outer disk and a contribution from each of the disks. The end that relate to the baffle and the one that comes from the bottom. This is what Cauchy's integral theorem looks like. So there's our contribution from the free surface, these x0, y0 terms. There's our contribution from each of the end baffles, and there's our contribution from the bottom. But now we do exactly the same thing as we've done before. The only thing that's going to change is how we're going to numerically evaluate them. So we do the same thing. So this holds everywhere, so it must hold on each of our surfaces. So it must hold evaluated on the free surface, it must hold evaluated on each of the end baffles, it must hold evaluated on the bottom. So if you do that, then what you end up with is n plus 2 complex equations, or 2n plus 4 real equations. And here's an example. Here is that integral evaluated on the free surface. Here's an example of the type of thing you get. So there's our mean part that we had before. There's our Hilbert transform that we had before. And then we get these extra terms. These are sort of a bit like the Hilbert transform, but they're not singular in the same way. They're sort of known functions that depend upon the terms of the circle conformal moduli, the radius, and their centres. And these are fine. We know what these are, and we can evaluate them. So this is the free surface one. As I say, you've got another one for each baffle, and you've got one for the bottom. So you take real and imaginary parts, so you get twice as many equations, and then what you do is you just try and find functions try and find functions given one of these, the x naughts or the y naughts, etc. Or you can do it by having some of the x naughts and some of the y naughts and finding the others. We just try and evaluate this numerically. So before going on to consider the dynamic problem, where I'm actually doing the time integration of those equations, what I thought would be sensible to do was to just think about a kinematic problem. Could I actually find this mapping? Is it possible to find it quickly enough so that I could do the dynamic problem? So first of all, I said, right, I'm just going to assume that I've got some free surface. This is our eta, or f of x as it was called. I'm just going to prescribe it. I'm just going to give it some amplitude a times cos pi x. Just something simple. So I'm going to give it some free surface, and then I'm going to say, right, can I determine this mapping? So now I've given it some free surface, what does this mean in terms of our y naughts? Well, it means I know what y naught is. That's the free surface. I know it along the free surface. These y1 tildes, well, these are the baffle positions, but they're the baffle positions in the map domain, so I need to update those iteratively, but I do know those because I've given them some initial guess. And then y tilde, that's the initial guess for the bottom. So I've got that, and I'm going to update these, but I do know what all these are at any given iterative step. And then we need to calculate the corresponding xn's. So I haven't really written down the numerical procedure for it, but I'm just going to talk you through it. Basically, what you do is you discretize those integrals using trapezoidal rule and equally spaced grid points, because if you then evaluate Cauchy's theorem at the midpoint of those grid points, then these principal value integrals that appear are just evaluated like the normal trapezoidal. Symmetric, so you can just evaluate them. You evaluate them at the midpoint, it removes the singularity. This is a technique that was used quite a bit by people like Jean-Marc Vandenbroek. He was doing these sort of trying to find nonlinear solutions to the wave problems. He'd write down Cauchy's theorem and then use this type of approach. So I thought I'd give it a go and see if it works. And it does work. So you iterate, each time you iterate to find these xn values, and then you have to do a few checks as to you've conserved mass and you've got the right, these values give you the correct position of the baffles and the bottom in real space. And then you keep doing this iteratively, and these then fix these conformal moduli. So just as a reminder, this h hat is equivalent to q hat. So we're doing the same thing, it's just harder, it's just more complicated. You've just got more things that you need to determine the position for. Okay, and here's an example, a couple of examples of what these maps look like. So here's our physical domain, and then you've mapped to this circular domain, and then you have to map back. So what was one of the pains of this method, and there's not a lot you can do, is that the Schottky-Klein prime functions that you want to use are really good from going from this domain to this domain, but there's no inverse functions to take you from this domain to this domain. That's why you have to do these things iteratively. So you sort of have to guess where you think this circle and its radius and its position need to be. You map it out and then you do it iteratively until you get this configuration. So it's a little bit tricky, but they're really nice. I mean, the fact that it works is brilliant. It's just, you know, it'd be nice if there was an inverse function to probably save you a bit of time. And you can do multiple baffles. Here's the two baffle case, two baffles on the left-hand wall. Remember, this is the actual physical domain is just half that domain. So two baffles on the left-hand wall, another two baffles on the left-hand wall, baffle on the left-hand wall, baffle on the right-hand wall. And you can do more.
So hold on, in this construction then, you're really just doing a conformal mapping construction, aren't you? Because you're basically giving us...
In this case, I'm saying, right, I want to see, can I construct that conformal mapping quickly, efficiently? If I can do that, then I can do the dynamic problem. And that's sort of the last slide, really, is what I want to finish with, is the dynamic problem. It's what I've been working on partly whilst I've been here. And I think I've just about now got something that works. But there are a few questions to sort of deal with. So that feasibility study shows that the dynamic short problem should be doable. There are a few issues so that didn't come up in the case with no baffles, really. So one question is, what you really want to solve your PDEs is to have equally spaced grid points along the free surface in the mu domain. But that doesn't translate to equal spacings in the theta domain, whereas you want equal spacings in the theta domain because you want to evaluate these Cauchy's integral theorem, you want to evaluate them with equally spaced grid points so you can utilize this midpoint, this midpoint on the principal value integrals. So I mean, it's not really an issue, but it's a small issue that you then have to do interpolation at each step. You have to interpolate first of all onto the theta points, do your integrals, get your x naughts and etc., and then you have to then interpolate back onto these fixed eta points. Will this cause issues? I've just sort of posed the question more than anything. I think the answer is not as much as I thought it would do when I started coding it, but obviously it's going to introduce some form of error. Is it going to cause you a problem in the long run? I think the answer to that is probably no. And then there's really two problems that I'm now currently looking at. So I'm coming back to this f of t that I said was either prescribed or you determine it as part of the analysis. So at the minute I think I've got the prescribed problem working. That seems to work quite nicely. The dynamic problem requires just a little bit more thought because, so here's an example of the type of equation that f could satisfy. So this would be a case where you've got a vessel, solid wall, spring with some linear coefficient, nu, probably the wrong notation to use. This is maybe a nu hat. This is some spring coefficient now. And F satisfies a spring type equation. So this is the vessel mass, the fluid mass. And this right-hand side is then your force on the vessel walls due to the fluid. So it's this surface integral is equivalent to integrating the pressure along the side walls. So this integral needs to be evaluated. And I did one of these coupled problems for the finite bottom case. And there I wasn't really thinking about it, and I just said, well, I've got the Fourier representation, so it's no effort at all to find points everywhere in the interior, and I just did this double integral in the mu space. When you've got baffles, it's going to be a little bit more problematic because you have to make sure you go around the baffles. But actually, I think it's now quite easy because when you write this down in the mu space, then it looks like you can use Green's theorem, which takes your integral over the interior to just being an integral around the boundary. And then your boundary on the two sides, you've got the symmetric flow at those 2 points, and so you can show that those integrals are just 0. And so I think it winds up just being line integrals along the surface, the bottom, and each of the baffles. And so if that then turns out to be the case, it should be relatively straightforward to go on and do this equation. Basically, all you then have is, as well as integrating those fluid equations, you have to integrate this type of equation at each time step. Okay, and that's where I've got to, and I haven't done this one well, since I've been here, but I say I think I've got the force dynamic problem now working. So it's a little bit slower than obviously not having any baffles in, because there's an extra element of iteration needed, because you can only do your client functions in one direction, or numerically in one direction, I should say. But yeah, it does seem to be working. I just need to play around a bit more. So thank you very much.
Thank you very much. Any questions? Yes.
So in the absence of forcing, does the problem have Hamiltonian structure?
Yes, if you want to just do the free sloshing problem, you mean, so that you've got
You just have a container.
just a
and
container that's fixed, and
Yeah,
then you
perturb-
shake it and
yeah.
then you stop it. Yes, in that case you do. Yes.
Can it somehow be exploited in the transform plane to
Good question.
a method that would preserve some properties?
Good question. I guess the answer is not sure, but quite possibly it might be something worth looking at. Yes. Yes, interesting thoughts.
For the problem without lateral boundaries, some of the most efficient methods for the boundary problem.
Yeah.
Exploit the Hamiltonian structure.
Yeah. No, that's a good question. Something to think about. I certainly didn't do that, but that's not to say that it wouldn't be useful.
What kind of regularity assumptions do you make on your free surface? I think you got it, I forget, eta, the function.
I mean, you just want it to be, I'm not looking at any cases where you have multiple valued free surfaces, although you can, because it's obviously parametric. You just want it to be, to have a 90-degree angle at the wall, pi over 2 at the wall, so that you get the right,
So you want a liquid that doesn't slosh too much? Is that the...
You certainly don't want it to splash. You don't want it to splash. You don't want it to steepen too much. You can, I've used this method on, so obviously the shallower, so if you have relatively deep layers, then this doesn't happen. But when you use shallow layers, you get these sort of wave steepenings. And then, I mean, as soon as it turns over, I think, Pavel was talking about this. You can capture it, but obviously as soon as it touches, then
Well, if it touches it.
as soon as
Is it just a technical difficulty or a fundamental limitation? I mean, the situation with overturning waste, where the elevation function is no longer single valued.
I think that's I mean, obviously it happens in the experiments, but we're more interested in those cases where you've got moderate amplitude, where you don't have this happening. But I mean, it would capture overturning up to the point where it touches, but then obviously
Because he's,
to stop.
I mean, there's no, because it's basically conformal mapping.
Yeah, that's what I
Yeah.
You should be able to capture,
Yeah.
when it overturns and touches.
Yeah.
Would you get the 120-degree wave, or is that
The Stokes wave.
Stokes, or is that a different
I think other people have tried to get these. I think there are papers on it. We haven't tried to do that.
But in theory, if you
but-
just increase the amplitude, you would get to that, would you?
Should do.
Whether you
Should do.
just have a
Or you'd approach
greater
it.
curvature near the
Yeah,
top.
yeah, it would smooth off at the top. You should do.
That might test your code in a nice way, to see how far you can take it. Anyway, I'm just,
That's
being
true.
very-
That's
yeah,
true.
okay.
Yeah. Absolutely.
Rob first, then Tom.
What's the motivation for looking at baffles?
Well,
Does it dampen things down? or-
that's the thing. That's the theory. Yes. I mean, I thought it was just an interesting problem. I just wanted to try and utilise these conformal mappings, see whether you could do anything fun and interesting. But you're right. So my interest in these problems relates to things like wave energy extraction in the deep ocean. These have connections. They're not the problems we're looking at in the closed vessels, but you can have similar open-ended vessel problems where you allow waves to come in. And then there's a question as to whether these baffles will help possibly with that. But in these cases, it should be a dampening effect. As I say, having not done, I mean, there are people who've done sort of CFD simulations of these things, and that's what they tend to find. But you know, I want to try and approach it from
And would it make any sense to have vertical?
a vertical.
baffles?
You could do that as well. You could. I haven't done that one, but you're right. You could certainly have a vertical one.
But you wouldn't expect a dampening effect from those.
So there were some papers on this. I remember reading. I think it doesn't necessarily have to be a dampening effect, but I think sometimes that is what they do see with
Reaching close to the surface.
Yeah, I think as you approach the surface, then
Like coral, or you know, you can. Darren, you've done this. Or maybe John Chapman's done something like this.
possibly,
You
yeah.
have like a periodic array of these
Yeah.
vertical baffles, and they might mimic coral. Also, like
Any fractal-like baffle shape, since we're talking about coral?
well, no, I think you're a long way away from
We're not.
that. So probably not at this point.
Yes, you could certainly do that as well.
But then this the numerical challenge, the more detailed the configuration would be.
Well, the point is, the more baffles you put in, obviously you have an extra equation you have to solve. So, and you've got you've got sort of, I don't know, 400, 500 grid points around this circle, and you've got to evaluate each of those, you equation each of those points. So you have you soon run up to sort of 2,000, 3,000 by 3,000 matrices. So obviously, the more you put in, the more of these equations you're solving, and then everything slows down. So I think sort of 5, 6, 7, 8, 9, 10 might be possible, and then it would start to, so but 100, well, yeah, it would really slow things down.
Is there any problem when you extend the domain, the surface won't be differentiable?
That is
So
the
you'll
one. That
lose
is
a little regularity. You might be lucky because they'll always end up right on the grid point. So.
that is one small issue that I sort of skated over, if you like. But in the force problem, you do get that. In the force problem, you get this sort of discontinuity gradient.
Yeah, but it gets very steep.
And what you tend to find is that for a few of the first few sort of time steps, you see you start to see one of your functions is almost discontinuous. I think it's the solid-free surface. But then it starts to smooth out, and it doesn't seem to be a problem long term. Because if you compare the results, I haven't done it for the baffles case, I've got no exact solution to compare against, but in the finite case, you have exact or asymptotic solutions to compare against, and it just seems to have be no issue at all. But yeah, that is something that I think you have to be a little bit careful about. Although saying that, it doesn't seem to cause any problems. But you certainly got to know that happens in that case. I think in the forced case, in the dynamic case, don't think that's quite so much of an issue because your vessel moves as well, and I think it's less of an issue. But in the forced case, it does happen, and that's from this XF double prime term.
Any more questions? Yes.
Sorry, what happens when the baffle is exposed, in the sense that there's no fluid?
Well, it depends. I mean, if you're just doing small enough amplitudes that, are you thinking horizontally, obviously all it does is just makes your floor, your bottom a bit higher. If you have one on the bottom and it protrudes out, as long as you don't allow fluid to go over, then you just got to couple two domain properly.
But then the baffle is outside the fluid domain. Oh,
in that case,
on the boundary.
Okay, so we did some work on this because this is an easier problem to do because basically you've got two separate domains. Those are linked, so the force on one wall plus the force on another is the total resultant force for your vessel. If you had a case where the baffle was only just precluded, I'm not sure how you could deal with that, because obviously you'd probably have fluid transferring over to it, but then it would preclude it. In that case, I don't think this method would work then. You'd probably have to do something else more clever.
Okay, well, let's call it a day and thank Matt again.
Thanks, everyone.